Describing a single cup of coffee requires an immense catalogue of physical data. To capture its state perfectly, you would need to track the position and momentum of every water molecule, sugar crystal, and caffeine particle, a chaotic web of trillions upon trillions of variables. A black hole is the violent endpoint of that complexity. It is the remnant of a massive star that has collapsed under its own weight, crushing all of its constituent matter into a single point. Yet the physics of these objects is shockingly sparse. A black hole can be described completely using only three numbers: its mass, its spin, and its electrical charge. Two black holes with the same three values are mathematically identical regardless of what they were made of, whether one formed from a collapsing blue giant and the other from a billion tons of household objects. They result in the same physical state. Facilities like LIGO now observe these collisions in real time, detecting the gravitational waves emitted by these simple, smooth objects as they merge. This creates a profound tension in physics. The most extreme object in the universe is also the simplest, suggesting that a black hole might be a place where information goes to die. Quantum mechanics is built on the principle of unitarity, which holds that physical information is never truly destroyed. The state of the universe at any moment must contain all the data necessary to reconstruct its past. Consider a book being thrown into a fire. While the ink and paper turn to ash, the information within the book is merely scrambled into the resulting smoke, heat, and light. If you could measure every photon of heat and every particle of smoke, the laws of physics allow you to run the clock backward and perfectly reconstruct every word on the original pages. The problem arises when that same book falls into a black hole. Once it crosses the event horizon, that information is no longer accessible to the rest of the universe. This forces a choice. Either black holes are the ultimate delete button for reality, or the universe has a way of hiding its memory that we have yet to discover. In 1974, Stephen Hawking published a calculation that upended our understanding of the void. He demonstrated that black holes are not perfectly black spaces. Intense curvature near the horizon distorts the quantum vacuum. Particles emerge spontaneously from this warped region, creating a faint glow known as Hawking radiation. This radiation carries energy away, and bit by bit the black hole loses mass, slowly shrinking over a time span billions of times longer than the age of the universe, roughly 10 to the power of 67 years, until the black hole will evaporate completely. This evaporation turns the information problem into a crisis. If the black hole disappears and the emitted radiation is purely random, the original data is gone forever, breaking the very foundations of quantum mechanics. For nearly 40 years, physicists struggled to prove that Hawking radiation isn't random, that it secretly carries the missing information back out into the universe. However, forcing the information to escape creates a mathematical conflict at the event horizon, a problem known as the AMPS firewall. The math suggests if information leaks out, the event horizon becomes a violent wall of high-energy particles that would incinerate anything attempting to cross it. This forces a direct conflict with Albert Einstein's general relativity, as his theory requires the event horizon to remain a smooth, unnoticeable boundary. In 2019, a series of papers using a new calculation called the island formula provided the first mathematical proof that the information does, in fact, escape. This is the Page curve. To save quantum mechanics, radiation entropy must rise, then decrease as hidden information reveals itself. The 2019 calculations tracked this perfectly, showing that as the black hole evaporates, trapped information transfers to the outside. The island formula suggests that specific regions deep inside the black hole are mathematically the same as the radiation floating outside of it. They are effectively two parts of the same whole. While this proves the data survives, it leaves us with a deeper mystery. How can 2 points in space be mathematically identical if they are separated by an event horizon? Resolving this without creating a destructive firewall requires a new understanding of how the universe is constructed. Classical physics treats space as a smooth, empty background, but at the quantum level, this plane is simply the surface of a deeper network. If the interior of a black hole and the radiation outside are mathematically encoded together, it implies they are physically connected. In this view, space is an emergent tapestry woven from a network of quantum information links, much like how the visible interface of the internet emerges from a web of data cables. This means the inside and the outside of a black hole were never truly separated by distance. The information remains connected through these underlying quantum links, allowing the data to bypass the event horizon as the black hole evaporates. The black hole functions as a cosmic magnifying glass, revealing the informational code that weaves our reality together. Understanding its paradox is merely the first step toward finally seeing the pixelated fabric of the universe itself.